Again, welcome to another show of New Hampshire Citizens for Progress. Today's show is going to be on fossil fuels. Basically, the science is not in disagreement that we have facing a climate change and that humans are a good portion responsible for this, and we need to take action. So it's really a political problem. I got a couple guests here that are going to discuss this with us, and I'm going to let them introduce themselves in a minute.
Hi, I'm Professor Sam Miller. I'm a professor of meteorology at Plymouth State University, and I'm an AMS certified consulting meteorologist. This is a diagram from a paper published by the Proceedings of the National Academy of Sciences back in 2018 by Stefan et al. And it describes the global climate system of the last several tens of thousands of years as a combination of the glacial, interglacial limit cycle, which ended with the beginning of the Holocene about 11,000 years ago and takes us up to the present, this point right here, in a period of time that we're calling the Anthropocene, when human beings have become the dominant forcing feature in the world's climate system. And we are left with two possible futures. One, a stabilized Earth, which is going to require a significant amount of actions on our part, or we can continue along the same path and pass through a series of planetary thresholds and land in a hothouse Earth.
Hi, I'm Joel Huberman. I'm a retired biochemist and molecular biologist and also an amateur climate scientist. I'm also a member of Citizens Climate Lobby, a volunteer for Citizens Climate Lobby, about which I may talk some more later on if we have time. What I want to say right now is that a good portion, not all, but a good portion of the science that goes into the graph that Sam just showed you was developed in the 19th century by scientists who were in it for the curiosity. Certainly not for the money. They didn't get paid at all. They did it on their own funds, and certainly not for politics. Those scientists started off at the beginning of the 19th century by the famous mathematician Jean-Baptiste Joseph Fourier. And what Fourier contributed was the mathematics of heat transfer, as well as the understanding that there's something about the Earth's atmosphere that traps heat and allows the Earth to be warmer than it would be if it weren't for the presence of the atmosphere. And the next scientist in line was an American woman named Eunice Foote. Eunice was not an aristocrat, unlike the other guys I'm going to be talking about. She was a middle-class woman, but with a strong intellectual curiosity. She did experiments and was the first to show that carbon dioxide is a component of the atmosphere that traps heat. She also pointed out that if more carbon dioxide went into the atmosphere, the Earth would warm. So Eunice Foote is the scientist who should be credited with the first basic understanding of the greenhouse effect. She was followed just a few years later by John Tyndall, an Irish scientist working in England who was an aristocrat and had access to lots of fancy equipment. And with that fancy equipment, he showed that not only carbon dioxide, but also water vapor and methane are greenhouse gases. And he too pointed out that putting more of them into the atmosphere would warm the Earth. Another important link came from Joseph Stefan, a Slovenian scientist working in Austria. He did a lot of measurements of the energy coming out of bodies that were at certain temperatures, energy in the form of heat radiation. And he showed that there was a relationship between temperature and amount of heat radiation, and that relationship became known as Stefan's law. The last of the scientists I want to talk about is Svante Arrhenius, a Swedish scientist who used Stefan's law and a hand calculator, not a digital calculator, it's called a slide rule, to calculate how much the Earth would warm if the amount of carbon dioxide in the atmosphere were doubled. He did his calculations and with a very crude climate model and concluded that the Earth would warm by about 4 degrees Celsius, which is about 7 degrees Fahrenheit, if carbon dioxide were doubled. His estimate is very close to modern estimates, which have a range of 2 to 5 degrees Celsius. And there you are, ladies and gentlemen. All of the science behind the greenhouse effect was worked out in the 19th century, no politics involved.
So the diagram, again, it's from Stefan et al., 2018, published by the Proceedings of the National Academy of Sciences. It contains a lot of information. I'm going to walk you through it carefully so that we can all understand it. First of all, let's take a look at the axes. The axis coming out of the page here is labeled time, with the distant past here and the near future located here. The vertical axis is the stability axis, with the top being an unstable climate condition and down here towards the bottom being a very stable condition. And finally, left to right, the horizontal axis here corresponds to temperature, with cool temperatures on the left and much warmer temperatures over here on the right. So let's go back to the beginning here, the glacial interglacial limit cycle. So a little bit of background on that. Until the beginning of the Holocene, we were in a geological era called the Quaternary, which began about 3 million years ago when North and South America collided, creating the isthmus of Central America and essentially cutting off direct circulation between the Atlantic and the Pacific Ocean basins. So we don't really have time to go into all the details of it right now, but what I will tell you is that set up a cycle of, and it was an unstable cycle that was driven primarily by astronomical forcings referred to as Milankovitch cycles. Things such as the shape of the Earth's orbit, the tilt of the axis, where in the orbit the lowest point was, known as the perihelion. But the net result of that was that there were long ice ages lasting on the order of 110 to 120,000 years, which were very stable and quite cold. And then there were short interglacial periods. And what you can see is that you have this small valley for an interglacial and a deeper valley for a glacial, indicating this was a very stable condition. And this was a much less stable, but a somewhat stable condition. So this pattern continued for about 3 million years. We have the last 2.5, let's say 1.5 million years of that understood pretty thoroughly. The most recent ice age began approximately 140,000 years ago and lasted about 120,000 years. The previous interglacial was called the Eemian. It was a period in the distant past when the climate resembled what it looks like today. But the last ice age ended in what was called the last glacial maximum about 20,000 years ago. And at that point, the Milankovitch cycles, the astronomical cycles, began to force the world up this kind of hill of instability, and then it dropped into a temporary interglacial. So what we know, again, is that glacial periods last on the order of 120,000 years, and the interglacials, the most recent being a period that we call the Holocene, they're about 1/10 that long, on the order of 10 to 15,000 years. So what you can see now, if we start to come forward in time, the stable valley that was labeled as the Holocene back here disappears. And this is what Joel was talking about, is that we have essentially changed the chemistry of the atmosphere and then the radiative forcing. And so that relatively stable point of an interglacial has vanished, and we've dropped into a new valley. So at that point, the point at which human intervention in the atmospheric chemistry and therefore its radiative balance became dominant, we began a new period of time called the Anthropocene. Anthros for human being. But at this point, we are no longer in the stable valley of the Holocene, and according to these authors, and they represent the consensus of the science, is that we're now looking at two possible futures. If we were to continue as we are now, we will pass through a series of planetary thresholds, and I can talk about that in a little more detail, and drop into another very stable situation called the hothouse Earth, when temperatures are somewhere between 5, 6, perhaps even 7 degrees Celsius warmer than pre-industrial times. There is an event very similar to this that occurred in the distant past called the Paleocene-Eocene thermal maximum. In that case, it was triggered entirely by natural means, a methane feedback that ultimately was probably traceable to a meteor collision, but it was 55 million years ago, and so it was therefore rather difficult to pin down exactly what the cause was. But the point that I wanted to make here was that there is a point beyond which any intervention on our part will not make much of a difference. The world will continue to warm on its own. And according to these authors, Stefan et al., co-authors, that point, this threshold point, can exist at temperatures as low as 2 degrees Celsius above pre-industrial, and we are now at something about 1.2. They also point out in their conclusions of their paper that we may have already achieved the necessary carbon dioxide concentrations in the atmosphere to carry us right through that threshold. So it isn't clear exactly where along this line we currently are. The other possible future at this point, here referred to as Earth System Stewardship, would be rather dramatic interventions on our part. And I'm talking about World War II scale of effort to fundamentally retool our entire economy, the energy system, transportation, agriculture. It's fairly fundamental. Tinkering around the edges isn't going to work. But you'll notice also that the closer we get to that threshold, the sharper the turn has to be. But as we make these interventions, hopefully we can recreate a Holocene-like climate within the Anthropocene that will have some degree of stability. We can talk further at some later point, if you like, about the types of interventions that are going to be required. But simple electrification or putting a price on carbon and leaving it at that, that's not going to be sufficient. We're talking about a much more fundamental change, and it has to be global in scale. It has to involve every level of government, from local all the way up to international, and it's going to require a lot more cooperation than we've been able to deliver up to this point.
Okay, taking a look at that, and from what Sam just explained, it seems like what's being presented by climate activists and some of the people running for office, such a thing as a Green New Deal, where we try to redevelop and retool our efforts instead of fighting each other. Maybe we should pick the common enemy as climate change, and that we might work together to accomplish that task. Many of these things involve other means of electricity that are becoming more popular and more financially feasible at this time, whether it be wind generation, solar, or even passive geothermal in the design characteristics, as well as using heat pumps. It seems like the electric heat pumps are capable of facilitating our comfort within our residences, and they run on electricity. So our major goal, stepping away from fossil fuels, should be the production of electrical to satisfy those needs. Would that be a pretty good synopsis that you might both agree with?
I'd like to comment. You want to?
I'd like to comment also.
Okay, would you like to go first?
Why don't you go first?
Okay. I think the point that I would like to make is simply switching our energy source to electricity generated by renewable means, wind, solar, geothermal. That's not going to be enough. We have to make much more fundamental changes than that. We have to reduce our carbon footprint to essentially zero within a decade or two, and we might have to even go into negative numbers to try to reduce the amount of carbon dioxide already in the atmosphere, with the hope that we can back away from that planetary threshold. That's going to require fundamental changes to the way we produce food, produce all of our manufactured industrial goods, so the way we move things around, the way that we store things, the way that we refrigerate things. It's a pretty fundamental difference. It's electrical or electrification of the economy. Certainly, that's a good start. It is far from enough on its own to be able to solve this problem.
Can I just go right into it?
Yep.
Okay. I want to introduce a tool here that's relevant to this issue. The tool is called En-ROADS. It's a tool that every one of you can use. There's a URL at the top of this chart, https://enroads.climateinteractive.org. If you just enter that URL into your browser, you can play around with it just the way I've been playing around with it. En-ROADS is a global policy simulation tool that will allow you to tell the effect of making changes such as electrification or a carbon price or other changes on the future energy use and future emissions and future temperature above pre-industrial of the Earth on a global level. Now, what you're looking at right now is the default. And over here on the right, on my right, your left, you'll see a bunch of colored curves. Each one of those colors represents a different primary energy source. Coal, gas, oil, renewables, nuclear, etc. And over on the right is a curve showing the predicted rise in temperature or change in temperature given the set of conditions that we set with the control knobs down below. Right now, all those control knobs are set at default values. So the temperature rise that you see here, 4.1 degrees Celsius or 7.3 degrees Fahrenheit, is the temperature rise that will occur with business as usual. What happens if we change the control knobs down below so as to change business as usual? Well, one commonly suggested alteration is to add in a carbon price. So in this graph, I have tweaked the control knob for carbon price all the way to its maximum, meaning a high price on carbon. And as you can see, that had an effect. It lowered our predicted temperature from 4.1 to 2.9. As you've just heard from Sam, 2.9 is still too much.
Yes.
So a carbon price by itself isn't sufficient. Now, let's try a different set of controls. Rick has suggested electrification. So in this graph, I have tweaked the control knobs for electrification in transport and electrification in business, in residences and industry. Is that what it is? Buildings and industry to their maximum. I have also tweaked the control knobs for energy efficiency in transport and energy efficiency in buildings and in industry to their maximum. So this is the best we can do in those sectors. And you can see that brings us from 4.1 down to 3.3 degrees Celsius, still not enough. But what if we put them together? So in this graph, what you see is the effect of combining a carbon price with electrical energy electrification maximum and energy efficiency maximum, and you can see that we got a stronger effect. Now the predicted temperature rise is only 2.4 degrees Celsius. Still not enough. But fortunately, there are other control knobs over here that we could play with, and I can tell you I've played with them, and by playing with enough control knobs, we can get things down to a temperature increase of 1.1 degree Celsius. We're already at 1.2. It's actually a temperature decrease. It just involves putting enough of the options that are available to us into play at a global level. It's a feasible change. We can do it, but it's not going to be easy. Hi. I would like to remind you all that the reason the temperature is warming, the reason the Earth is now in an uncertain position on the chart that Sam showed you, is because of the increase in greenhouse gases in our atmosphere. The increase in carbon dioxide in our atmosphere, the major greenhouse gas, carbon dioxide, has been tracked since 1958 in a very sensitive fashion by instrumentation developed by Charles David Keeling, a 20th century scientist who started his measurements in 1958 with his observatory on the top of Mauna Loa, a very high observatory in Hawaii. He started in 1958 when the amount, and he measured the amount of carbon dioxide in the atmosphere at that time as being 315 parts per million. It has now gone up to 414 parts per million as of the end of January when I made this graph. In other words, about 100 part per million increase since 1958. And you can see the rate of increase is increasing as we get closer and closer to the present. It's accelerating. Now, in the next graph, I want to go backwards in time with the same data. The Keeling curve for Mauna Loa, but beyond 1958 and going backwards, the data comes from ice cores. Inside ice cores, little tiny air bubbles are trapped, and scientists can actually measure the concentration of carbon dioxide in those air bubbles. And the layers of the ice core come well marked out, so the scientists know exactly what year they're measuring the carbon dioxide content of. And in this way, they can go back all the way to 1700, pre-industrial age. At that time, 1700, the carbon dioxide concentration was 280 parts per million. It's now 414 parts per million. And I think it's time now for Sam to tell us what the significance of that difference is.
If you look in these ice cores that he mentioned here, for example, one run by EPICA, which is the European project. There's another one from the Vostok Science Station at the Russian Antarctic Station, as well as some work done by the Climate Change Research Center at UNH. You can trace back fairly easily about 800,000 years through several glacial, interglacial cycles. And from that, you can get a lot of information. For one thing, you see a pretty tight correlation between the content of carbon dioxide or its concentration in the atmosphere and the temperature. There's virtually no lag time in between them, and the correlation coefficient is pretty high. They're very closely related. One of the other things you can get looking at that is the natural limits in the amount of carbon dioxide in the atmosphere during that 800,000 year period. And during the glacials, when the CO2 content crashes and the world cools down, that number hovers somewhere at around 180 parts per million. During interglacials of the past, for example, the Eocene, which I mentioned earlier, it goes as high as about 280 parts per million. So we see that the numbers from the Keeling curve measured at the Mauna Loa Observatory in Hawaii are well outside that natural range. And that record isn't unique. There are similar records, they don't go back quite as far, from Antarctica, the actual South Pole, all the way up to Barrow, Alaska. It's not called that anymore. Barrow has an Inuit name now that I cannot pronounce, but I'll just call it Barrow, Alaska. And they all showed the same upward trend, so it is not unique to that location in Mauna Loa. Could I also add that that's not the only greenhouse gas that's being added to the atmosphere? There's methane, which for a short period is about 85 times more powerful than CO2, as well as nitrous oxide, which is about 300 times more powerful than CO2. And methane is now becoming a feedback gas, which is one of the things that carries us over that threshold.
So I do want to emphasize that the increase that we've seen from 280 parts per million in 1700 to 414 parts per million today is entirely due to burning of fossil fuels and also to removal of sinks, of ways of getting rid of fossil fuels. For example, when we cut down trees, we are removing fossil fuel sinks. The combination of removal of sinks and the burning of fossil fuels, all human activities, are what's responsible for the rise in carbon dioxide. Let me repeat. The major greenhouse gas is carbon dioxide. Its rise is due to the burning of fossil fuels. If we want to get back to a comfortable climate, we're going to have to stop burning fossil fuels.
Fossil fuels are not the only greenhouse gas that we're concerned with nowadays. There are two rather important ones. One of them is methane. Methane comes out of melting permafrost or methane hydrates at the bottom of oceans, but it's a feedback gas. So in addition to humans adding methane through industrial farming, methane is also being released now from these other natural sources of methane. Methane, for a short period, is about 85 times more powerful than CO2 in terms of its warming ability. After between 12 and 20 years, it breaks down into carbon dioxide and water vapor being another important greenhouse gas that's about as powerful as CO2 unit for unit. Another one is nitrous oxide. Nitrous oxide is about 300 times more powerful than CO2 as a greenhouse gas, and it's in much lower concentrations because it doesn't require very high concentrations to be an important warming effect. And we now think that about 7% of the additional warming that's occurring is through the addition of nitrous oxide, both from industrial processes and natural processes, including some of the feedbacks. So I'd like to say one more thing about the feedbacks. The permafrost that rings the North Pole through northern Canada, Siberia, the Nordic countries as well, Scandinavia, this methane is now melting. NASA has documented this. You can look up the Drunken Forest, for example, and you see trees falling over because their root systems were standing on permafrost. But that permafrost contains, and within the frost and below it, very large reservoirs of methane from ancient forests that have died and rotted away, and that methane has been trapped down there. So we're now seeing large methane releases coming out of the permafrost. That in turn is causing the excess amount of warming that we're seeing in the high Arctic, which you know is warming at a rate of 2 to 3 times more rapidly than lower latitude areas. The same thing is now happening with nitrous oxide, unfortunately.
There's another point I'd like you to delve into a little bit. There seems to be quite a bit of confusion in regards to climate and weather. And as a former meteorologist, can you say how all this, what's taking place is affecting our climate?
Thank you for that question. I started out as a weather forecaster in the Air Force during the 1980s. The weather forecasting game is quite a bit different than climate. Climate forecasting, you can essentially project average conditions out, giving a certain set of assumptions. For example, the level of sources and sinks. That's the most simplified way of thinking about it, with sources ultimately being industrial processes, as well as feedbacks, sink being various removal mechanisms that you can assume are there or are not there. So you can project that out centuries into the future, and it essentially represents the average condition at a particular point on the surface of the Earth. Weather is variations around the mean. You can think of it as the kind of the turbulence or the uncertainty in the larger scale forecast. You can make a weather forecast out usually to a fairly high degree of certainty about 5 days into the future. And by using a process called ensembling, where you run one model 30 or 40 times and then combine it and find the average condition, you might be able to push that out 2, possibly 3, but 3 weeks is really pushing it. By the way, if anybody says they can give you a weather forecast 90 days into the future, they're lying. Okay, you really can't go beyond 2 weeks with any real certainty at all. And really, the certainty is pretty much at an end at about 5 days. And again, you might think of that as variations around the mean climate condition. There is another metaphor that you can think about. Climate tells you what clothes you have in your closet. Weather tells you what you're wearing that day.
I like that analogy. Okay, well, I want to thank everyone for watching this show. We didn't get to cover the acidification of the ocean or the change in weather patterns, because one of the things about the climate change we're experiencing is that we're unable to specifically say what its effects are. What we do know in general is that the storms, different areas are changing, storms are more intense, and the amount of damage being done. We've seen that with the hurricanes, tornadoes, Australia burning, California burning. There's plenty of evidence to show the negative effects. Hopefully we act together as a group, like the space program, where we decided we had to accomplish this. We put the best minds together, we worked on it, and we got it done. Well, thank you, take care, be well.